Okay, then I'm going to go ahead and start. Can somebody confirm if you guys can hear me? Awesome. Okay, so yes, today we have a special session talk here about our paper titled Feeding Hungry Models Less. And the topic is specifically about applying deep transfer learning for embedded memory PPA models. So at Intel, I work in a team where we provide a tool to optimize memories. So designers use our tool with the goal to optimize the power, performance, and area of their embedded memories. So this is the overall goal of our tool. That's always what we're trying to do. But we're going to look at a little piece of that, and I would like to take you through a little story to understand what specifically we're working on. So whenever we want to optimize something, we typically require a fitness estimation. So we want to know how good a certain solution is. And here we see a job for supervised machine learning. So maybe you know this type of setup already from a previous talk. It's also very similar to some of the other things we have seen so far. Basically, what we're trying to do is we predict some y as a function of x. And here on the left, we have our MIS model, which is a neural network trying to learn this mapping from x to y. And x in our case are parameters of embedded memories. So typically we have up to around 15 parameters describing the memory, such as the number of words, the word length, or how many banks we split our bit cell array into. In addition, we have a few operating parameters and process variability. So here you can see the process sketched out as typical, slow, and fast corners. And in addition to that, we would feed, for example, the voltage with which we're operating or the temperature. From these input parameters, what we try to estimate are PPA variables. So these are, for example, the area, dynamic power consumption, static power consumption, and the performance or frequency. Now, as you can see in the headline of the scroll, basically this data set of x and y, we obtain this for a certain technology node, a certain compiler vendor or EDA vendor, a certain type of compiler. So this typically includes the type of bit cell and some kind of PPA preference. So here we have a speedy RAM, so a RAM compiler which is optimized for frequency. And lastly, we also get different versions of the same compiler. So in this case, we have version 1. And a few times a year, typically, depending on the vendor, of course, and how current this is, we get new versions for each compiler. Now, I want to make sure that what's clear here is that we're looking at a subsection of the problem. So overall, I said on the previous slide, we're trying to optimize the PPA of embedded memories. And now I'm telling you, well, this is supervised machine learning. Really, what I mean is, when we try to optimize, we have potential solutions to our optimization problem, which we, in a loop, evaluate and then try to improve a little bit until we evaluate again, and we keep going in this loop. Now, you can see here in the top right, the evaluation is what we use supervised machine learning for. So to compute our fitness, to compute the suitability or the PPA, in our case, of the embedded memory, that's where we bring in supervised machine learning. And another important thing to note is that we don't do this on the fly when somebody wants to optimize, but we have many designers using this tool, working on different products. And when we build this model, we don't know, which memories they're going to need. So we have to prepare this model a priori so that it can estimate the PPA for all possible memories that a compiler might be producing in whichever products we're using. So MIS model is not a single person. Miss Model actually are many different people. And the reason for that is that every time a new compiler or compiler version is released, a new map model starts learning from scratch. So you see here we have many different X to Y mapping data sets, and each of them is studied by a different model. And this is the current status quo that we have. So we have on the top left Miss Speedy RAM v1. This would be what we just looked at. Then there's another compiler version of the same compiler, Miss Speedy RAM v2, which may be the model we're training this month. Then we have other compilers like Miss Tiny RAM, which tries to produce, has a more of an area focus rather than a performance focus. Or we could also have the same or different compilers on different technology nodes. So here we have another Speedy RAM compiler for the 4 nanometer node. So yeah, like I said, status quo, we train a new model for every one of these. The problem is really that generating training data is expensive. So whenever we need to make such a data set mapping X to Y, what that means is that we have to run a so-called memory compiler. So memory compilers are used in the industry to generate embedded memories. This is very handy, right? You build a software once that can generate layouts given different parameters. And so whenever I want a memory that has a few more words or wider words, I don't have to completely reinvent the layout from scratch. Instead, I use the memory compiler and I tell the memory compiler what type of memory I want. But a lot of parameters go into this memory compiler that I might not know in advance, right? And this is really what we're trying to optimize. For example, the number of banks don't influence the interface I get from my memory, but it does impact the PPA, so I need to tune it. Okay, but back to training data generation. So we're trying to build this data set. And typically in the past, we have used around 10,000 observations in our data set. So 10,000 distinct memories that we generate with the memory compiler. And the memory compiler gives us layouts, etc., but also PPA simulation results or interpolations of simulation results. And so we have to do this about 10,000 times, and each run takes around 1 hour. Now, of course, we can parallelize a lot of this, right? We don't have to run in 10,000 hours. We can do a little bit side by side. But at the same time, we usually don't get a single compiler at once, but we get like 15 compilers in this one version bundle. And so we have to do all of this, which again decreases how much we can parallelize for a single compiler. And this results in around 4 weeks enablement time for us in practice. Yeah, we get a new compiler, we want to train a model for it, takes around 4 weeks just to generate the data. So how can we solve this? Now, Ms. Model is wondering, why can't models just share the parameters that they have learned? Because this, as it is not the society Ms. Model wants to live in. So the society as it is every model here is learning in isolation, right? They don't talk to each other. Everybody has their own data set. Now, Ms. Model envisions a world where all the models can talk to each other and they can share. And they can share what they have learned about their data, things that might carry over between compilers. For example, proportionality of area and leakage. Yeah, so basic correlations that exist in every compiler, but also maybe the strength of the correlation if we're talking of a transfer from version 1 to version 2. What this would mean is that Miss version 2 could learn from Miss version 1's mistakes. She would need to study less data. And maybe, just maybe, we could all finally spend more time doing what we love. So you will see here on the left, again, the status quo. We train a version 1 compiler with around 10,000 observations, which we feed into our network. We get some accuracy, right? This we'll see later, our target is usually to achieve an almost worst case accuracy of 95%. And as I said before, in practice, this takes around 4 weeks to generate the amount of data we need. When version 2 comes around, we do the same thing again. Now, in the world that Ms. Model envisions, when version 1 could learn from the data or the parameters of version, so version 2 could learn from the data of version 1, and in consequence, we would need less data, maybe in this case here, a quarter of the data we needed before, while keeping the accuracy constant, right? Because this is a quality criterion we cannot compromise on. And as a result, data generation being the most expensive part of the process, maybe we could reduce the time it needs to enable by 3 weeks. So how would this work? After studying the source domain being in this case here, SpeedyRAM version 1, Ms. version 1, so the model over here, transfers its parameters or its data to version 2. Version 2 says thank you and uses, in this case here, the data to learn on the source domain. And version 2 is our target domain. Hopefully we'll need less purple data, less version 2 data to attain sufficient accuracy. Right, and I hope that's clear. Basically, I mean, if we share the parameters, that's usually good enough, right? Because we just basically take a model that's already trained on version 1, then we continue fine-tuning it on version 2. If we don't have the model parameters for some reason, sometimes it's more practical to actually take the old data and train on that data, and then we do the parameter transfer after we retrain the first model. Both come down to the same thing is what I want to say. But Ms. 1 was not the only one who wanted to help Ms. V2. So now even the other technologies were beginning to see the benefits of knowledge sharing. What we just saw, the example, that was the transfer from the same compiler version 1 to the compiler version 2. So this is a straightforward transfer, knowledge sharing transfer, where we imagine that this would be a clear win, right? The previous compiler version probably doesn't produce drastically different PPA than the next compiler version. It's the closest thing we can think of. But sometimes we don't have the previous version available. Maybe we're trying to train version 1 right now. Or for some reason we didn't enable version 1. And then we could look at other sources. And in our experiments, we compare 2 different source domains. So we have the predecessor, version 1, the direct predecessor compiler. And on the right side here, we have the same compiler, but on a different technology node. This scenario we call cross-tech. So we transfer from one technology to the next. And yeah, hope this is clear. This will be used in the next slides because this is how we did our experiments. Of course, nobody would lose their job altogether. After all, everyone's experience is unique. What this is trying to tell you is that while we expect that there's a benefit of transferring parameters, we don't expect that just transferring the parameters from the previous version is enough to attain sufficient accuracy on the target domain. And what we see here is plots of, so distribution plots, kind of smoothed histograms of the different data domains that we have. So the dark green line is our target domain for which we want to enable our model. And then we have 2 source domains. The cross-tech is the light purple, and in dark brown, we have the predecessor domain. And you can see that the distributions are fairly similar, right? So on the left here, we see that all of the curves have a big bump on the left and then fall fairly smoothly. But also, they're not identical. I mean, we can see that the peaks are a little bit different. And also, our target domain actually has a little bump here that probably couldn't be learned by just training on the source domains. So this is for dynamic power. On the right side, we have another example for static power. And that's just to give you an impression about how similar are our domains? They're definitely not identical. And our experiments have also shown that, so we've tried just training on the source domain and predicting the target. It's not bad, but it's not enough. So that's why here no model will lose their job. Now, let's take a look at some results. So Miss version 2 appreciated everyone's help. Although Miss version 1's input helped her most to save time, she did thank the other technologies for achieving highest quality. And let's go into what this means here. On the left side, you can see the plot of our results in terms of mean error. So on the y-axis, we see the estimation error. And we always want to minimize the error, right? This is the inverse of accuracy. So ideally, we'd see 0. Then we have a black line in the plot, which is the baseline model. So this is trained in the traditional fashion, where we take all of the target domain data, completely ignore other domains, and we train on all that data, 100% of target data, and try to achieve the best accuracy we can with that learning. But for the other two lines in the plot, you need to look at the x-axis, where we varied how much target data we use. Right? So target data is the thing where we're trying to reduce it. That's what's expensive. I mean, all data domains are expensive, but we do have some source domains for which we already generated data. So ideally, we'd use no target domain data, but probably we should use some. And on the x-axis, we see varying amounts of target data used. So if we use 100% target data, that would mean we didn't really win anything in terms of enablement time. And that's our core goal of this work. And then on the other hand, we have most drastic is the reduction down to 10% of target data. And the orange line, this refers to the predecessor scenario. So we pre-trained our model on the direct predecessor compiler source domain. The blue line, we pre-trained on the same compiler from another technology node. Here on the right side, we have a plot that looks pretty similar at first until you notice the y-axis scale. So what we see here is the same error metric, but instead of looking at the mean, we look at the almost worst case. That's usually what we use as our quality criterion, because designers who look at predictions or estimates that are really, really bad don't care if you tell them that the mean error is pretty good, right? They care about what they see, and we want to make sure that 98% of what they see is good enough. So we look, or has a low error, so we look at the 98th percentile error, or almost worst case. Now we see the same lines here. I don't think I have to explain that again, but let's look at some conclusions here. So if we use 50% of the target data and pre-train on the predecessor domain, then we find that at 50%, we outperform the baseline. So given that we don't want to sacrifice any accuracy, this shows that we can go down to 50% of target data only. Up to 50% in general, we see that the orange line is always better than the blue line. So the direct predecessor generally needs less data to perform better. On the other hand, if we use more than 50% of data, it looks like the cross-tech domain is actually the better source domain. So this is important if our goal wasn't to reduce the amount of training data, but to reduce our error further. So if error reduction is the goal, then the cross-tech domain looks better. One hypothesis for why this happens is that a domain that is less similar to the target actually provides a better initialization if you want to generalize better. Right? It's not so stuck yet in some local optimum. And it's clear that the model has to be changed to achieve good accuracy on the target domain. And lastly, I'd like to point out here, if we look at the almost worst case error, our goal is usually to achieve an estimation error of less than 5%. So you will see that the baseline here is already much better than that. And that's because so all of the models here are absolutely trained with the same architecture, of course, but compared to our previous architectures, which we used to determine how much data we need to generate, we made very much, big improvements here. So probably we have a bit too much training data. But nevertheless, if we just consider the training data in absolute terms, for this one we used 13,000 data points. Then here we are able to reduce our training data in the target domain by 90%, down to 10%, meaning 1,300 observations only instead of 13,000, and we still outperform our target accuracy of 5% in 98% of the cases. And this is really what Ms. Model was hoping for all along. So she's very content now. She manages to achieve the exact same accuracy, or even a little bit better, if she reduces the target data by 50%. But if we want to just achieve the accuracy that we have, compared to our previous data needs, we are now at 90% reduction, needing only 10% of what we required in the past. So in practice, that means that instead of spending 4 weeks studying for a new compiler, models can now spend less than 1 week to train on a new compiler. That's 3 extra weeks of holidays. And so that's what Ms. Model is doing over here. But of course, the feeling, you go on holiday, you think you can finally relax, then you're lying there and you get a bit bored and you don't really know what to do with your time. And then you think about work. And so Ms. Model is thinking, what's next? What else do we have to explore? And there's several topics here. One thing that we didn't evaluate yet is what happens if you train on multiple source domains. Right, we train either with the predecessor or with another compiler with the same compiler from another technology. What would be the results if we mix that data? If we mix the data, should we maybe train sequentially, first on one domain, then on the other? Should we just mix it completely? That remains to be explored. Another question is, how can we know which source domain is suitable? Because normally what we did so far is we train on the source domain, then we train on the target domain, we check if it works. But this training is also somewhat expensive, as you know, so we would like to avoid it. Maybe there's some metrics about distance of the target and source domain that we can use to explore which source domains will be helpful and which we should rather not use. And lastly, in these experiments, we've used compilers that had the same input parameters and for which we've sampled the same PPA variables. But occasionally we start sampling a new kind of timing, for example. In addition to cycle time, we might sample the access time or the enablement time, different things. Also, compilers frequently get new parameters, in which case the X side of the equation would change. And in that case, we would have to see what happens if we replace the input layer of the neural network or replace the output layer of the neural network. How can we cope with this different data structure? So Ms. Model is happy. I hope you are too. Thanks for listening.
Okay, Felix. Do you hear me, Felix?
Yes.
Okay, I'm just trying to make sure that I know how to use the platform. First of all, many thanks for this great talk. So I think everyone would agree that you have very great skills in presentations. So I liked your storytelling and all those insights. We have one question from Daniel, but I would start with a very quick question from my side. It seems, and obviously this is not a customized solution for the problem of embedded memory. I can imagine you can apply this methodology and this, let's say, this concept for many other problems, but that could have a large impact. But do you have an idea, or can you comment on what is the challenges if we want to transfer this concept to, let's say, different kind of problems, or how general this solution? You are already working on this area, so maybe you can comment a bit.
Mm-hmm. Yeah, I think so. Of course, if you port this to different problems, then the data structure will be different. Maybe you have to use a different network structure. And when you go to different network structures, the solutions change a little bit. So I think we've seen a lot of presentations also last year on different transfer learning things. Generally, the method of transferring model parameters should be applicable in any domain.
Also, I also thought that. We have a question from Daniel. Can this be considered as an alternative form of ensemble learning?
Could you clarify what you mean by ensemble learning?
Well, I mean, so, Daniel, if you can speak up, that would be great.
Daniel, if you want to speak up, you just need to click on the bottom bar and then you're added. Or you can write your question, whatever you feel.
So I'm okay, no worries. So I'm thinking you're suggesting to connect, so ensemble learning, maybe connecting multiple models and voting on the prediction, perhaps. I'm not sure so much because, I mean, I was using different MIS models talking to each other in the slide, but really what we're talking here is just transferring parameters and then fine-tuning on the target domain. So maybe my analogy was a little bit misleading in that sense, or maybe I'm overlooking something, but I don't think so.
Okay, great. Maybe one quick last question from my side. That, let's say, the problem of generating the data or for this embedded memory, it's very well known and old, how to say, and deep learning is already there since also a long time. So maybe you can comment why it's now, or maybe it's long time when Intel or you or other groups are now to think about solving this problem in this way, like solving the hungry data, how to say.
So I think we've been struggling with it from the beginning, but first we had to focus on other things like how to get our accuracy good enough.
Okay, and then how to get rid of the data or reduce the data.
Right, yeah, that was the next step, right? First we try to make it work, we get a good accuracy, and now we have to save time.
Sounds great. Okay, so Felix, many thanks again for your great talk and for contributing to the special session. It's really highly appreciated.
Thank you very much.